So in the last lecture, we introduced the notion of the delta function, and we gave a very pragmatic introduction to delta function as being useful to model certain systems with an impulse or an input at a very specific interval of time, a very specific point of time, rather, not even an interval. And we did this by taking a rectangular pulse and then shortening the pulse and simultaneously lengthening the pulse so that we don't do anything to the area of the pulse, which we normalize to 1. And then in the limit that the width of this pulse goes to 0, you get an infinitely long peak, which we identified as the Dirac delta function. And we also talked a little bit about some of the properties of the delta function. The most important property of this is over here. If you use the delta function multiplied by some function g of t and integrate from 0 to infinity, the delta function basically picks out the value of the function at the particular point at which the delta function is non-vanishing. Okay, so in some sense, the delta function is used as a projection operator in a very rough, crude way of thinking about it. It projects out the value of the function at a specific value of t. Okay, and then we went ahead and worked out the Laplace transform of the delta function, and we found that this was equal to e to the minus as. Okay, and this is where we stopped. So today we're going to continue with this and work out a very simple equation. Work out a very simple example to illustrate how one can use this idea in solving a specific example. And the example that we're going to be doing is the same one we did for the square wave, except that we're going to put a delta function source on the right hand side. So the equation is y double prime plus 3y prime plus 2y equals delta t minus 1 with the initial y of 0 equals y prime of 0 equals 0. Okay, and that is just for convenience. You can choose your own value of the initial conditions. Okay, so if you remember, this is the exact same equation, except that yesterday we had a square wave on the right hand side, something like this, and we solved this ODE for this particular driving force. So today we're going to solve it for an impulse driving force. The driving force exists only at t equals 1, not nowhere else. And the only new input that we need is that the Laplace transform of the delta function is e to the minus as. Okay, so you can proceed the exact same way. Take the Laplace transform of both sides and understand what the Laplace transform of the second derivative is. Ly double prime is s squared times the Laplace transform of y minus s times the value of the function 0 minus the value of the function, but derivative of the function at 0. In this particular example, the value of the function, the value of the derivative of the function are both 0 at t equals 0. So this simply becomes s squared y. Okay. So plug everything in and you get Ly double prime plus 3y prime plus 2y. Right? Which tells me that s squared y plus 3sy plus 2y. That is the left hand side. And the right hand side is basically the Laplace transform of the delta function at a equals 1, which is e to the minus 1 times s, where I used this equation. And that's pretty much it. The rest is straightforward. This is our subsidiary equation. You invert this equation to figure out what capital Y is. And once you figure out what capital Y is, you can then take the inverse Laplace transform and figure out what little y of t is. So just for completeness sake, we will go ahead and do this problem because it will also help us apply what is called the T shifting theorem again. So y times s squared plus 3s plus 2 equals e to the minus s. And this, of course, is factorizable. So the inverse Laplace transform, the Laplace transform of the function that we are looking for is this. Okay, which you can quickly check for yourself that you can write as 1 over s plus 1 minus 1 over s plus 2 using partial fractions times e to the minus s. Okay. So since the inverse Laplace transform is also a linear function, I can take the inverse Laplace transform on both sides And this will give me the solution as formally the inverse Laplace transform of e to the minus s over s plus 1 minus the inverse Laplace transform of e to the minus s over s plus 2. Okay. So our job is to figure out what is the inverse Laplace transform of both these guys. So again, this is something that will be important in other problems. So please do pay attention to how to calculate the inverse Laplace transform of a function of this kind. So to do this, we will use the T shifting theorem, which basically tells you that if you know that suppose the Laplace transform of a function f of t is f of s, say, okay, then the Laplace transform of the function f of t minus a weighted by the Heaviside function is basically e to the minus s times f of s. Okay. Now I can invert this and I can use this to calculate the inverse Laplace transform of any function multiplied by e to the minus as. So I can invert this and say that L inverse of e to the minus as f of s, where f of s is the Laplace transform of the function f of t, is basically f of t minus a u t minus a. Okay. And I'm going to use this to solve this problem. How? Well, my goal is to figure out the inverse Laplace transform of e to the minus s over s plus 1, which I will write as e to the minus s times 1 over s plus 1. Okay, so if I pretend that this is my capital F of s, what is the function that has 1 over s plus 1 as its Laplace transform? The function that has 1 over s plus 1 as its Laplace transform is
e to the minus t.
E to the minus t, because 1 over s is the Laplace transform of 1, and since this is shifted by 1, I had to multiply by e to the minus t. So L of e to the minus t is basically 1 over s plus 1. So which means that L inverse of e to the minus s 1 over s plus 1 is, I'll use this formula, f of t minus a u t minus a. So this is basically e to the minus, instead of t, I should put it, a here is 1, so t minus 1 u t minus 1. This response is only for times greater than 1. Well, first of all, does this answer make sense? Yes, it does, because the driving force only exists at t equals 1. So whatever the effect of this driving is should only be apparent after the driving is done, not before. So you cannot have a response before you start driving the system. That will violate causality. So you should have a u of t minus 1 over there. Okay. All right. So similarly, you can figure out the Laplace transform of e to the minus s 1 over s plus 2. 1 over s plus 2 is, of course, the Laplace transform of e to the minus 2t. So this is e to the minus 2 t minus 1 u t minus 1. Okay. So put everything together and you find that your y of t is basically 0 for t less than 1. And for t greater than 1, this is e to the minus t minus 1 minus e to the minus 2 t minus 1. Okay. So that is how you solve inhomogeneous differential equations with a delta function on the right-hand side. It's rather straightforward. The only two things that we have used are what is the Laplace transform of a delta function and how do you practically use the T shifting theorem. Okay. So that is something that I wanted to work out in class. The next thing that we will do is to understand a rather interesting problem. And this goes by the name, mathematically, this goes by the name of convolution. And the idea is this. Suppose you know the Laplace transform of two functions. Let's call them f of t and g of t. Okay. So call the Laplace transforms, call them G of S using our usual notation. The Laplace transform is the capital letter of the letter used to denote the function, and it's a function of S and not T, of course. Sorry, F of S and G of S. Okay. Now, knowing F of S and G of S, you can construct the product. Construct the product H of S equals F of S times G of S. Okay. Now you can ask the question, what is the function whose Laplace transform is H of S? In other words, the Laplace transform of F of T is capital F. The Laplace transform of G of T is capital G. So suppose if I want to construct the function capital F times capital G, what is the function whose Laplace transform is this guy? Okay. If I asked you to guess, what would your guess be? So L of F of T is capital F. L of G of T is capital G. L of what is capital F times capital G? A straightforward guess would be it'll be the Laplace transform of little f times little g, but that turns out to be not true. Okay, so L of G times F is not equal to L of G times L of F in general. Okay. The answer to this question is not very easy to guess, and the answer turns out to be, answer is the convolution of F and G. It is denoted mathematically by, so let's call this H of T. This is F star G. Okay, of course, this whole thing is a function of time, and the way this is defined is integral 0 to T F of tau G of T minus tau d tau. Remember that tau is a dummy variable of index. I can call this X, for instance, or Y, or whatever it is, Q, R, whatever. Tau is a dummy variable of index. It's integrated from 0 to T, and so the right-hand side is also a function of T. Okay, so this is the function whose Laplace transform is capital F times capital G. Okay. So I will not prove this. The proof is found in a textbook, and it's relatively very straightforward, so you can always go look at it. But let us try and use this to solve a problem, and then I will tell you some nice properties of this convolution. Okay. So suppose if you're given, suppose you come across, practically speaking, some problem in your exam or something like that, whose inverse Laplace transform is a little difficult. So let us say that the question is find L inverse of A over S square times S square plus omega square. Okay. So this is the problem that is given to you. Now you can quickly look at this and claim that, oh, well, I can use partial fractions, what else and what not. Because if you decompose this into something like 1 over S or 1 over S square or 1 over S square plus omega square, all these functions seem simple enough. So if I decompose this into an addition of simple fractions, I might guess the inverse Laplace transform of each of these fractions. That is certainly one way to do this. The other way is to simply recognize that I can write this capital H as A over S square plus omega square. And I can recognize that this can be written as 1 over S square times, actually, let me make this omega, so it's even easier. Anyway, I have to divide and multiply by omega, so I might as well call this omega. S square plus omega square. Okay. So let me call that this is some capital F and this is some capital G. Why? Because in this case, I know exactly what the functions are whose Laplace transforms are 1 over s square and omega over s square plus times omega over s square plus omega square, right? So I know that the Laplace transform of f of t is 1 over s square, and the Laplace transform of g of t, if I choose g of t to be sine omega t, is omega over s square plus omega square. Okay, so I can use these two informations because when I look at this complicated h of s, I find that it is the product of two functions, each of which is simple. I know the inverse Laplace transform of those guys, so I can use that information to guess the Laplace transform, inverse Laplace transform of the product of these two functions. How will I do this? I will use the convolution theorem. So I know that L inverse of 1 over s square is t. I know that the L inverse of omega over s square plus omega square is sine omega t, which means that the inverse Laplace transform of the product of these two guys is given by integral 0 to t f of tau g of t minus tau d tau. F of t turns out to be just t, so this is 0 to t. Excuse me. F of t is t, so which means f of tau is tau. G of t is sine omega t, so g of t minus tau is sine omega t minus tau d tau. Okay. Now you can certainly evaluate this and get what the answer is. You can also, if you're looking at it for the first time, you will actually be a little confused because I have two functions, 1 over s square and omega over s square plus omega square. I could have written this as omega over s square plus omega square times 1 over s square. And I could have pretended that g is 1 over s square and f is omega over s square plus omega square. In which case, the definition of this would be the other way around, right? The answer is it doesn't matter. So this is one of the properties of the convolution. F convolution of g, which is defined as f of tau g of t minus tau d tau, is equal to g convolution of f, which is equal to 0 to t g of tau f of t minus tau d tau. It doesn't matter which I call g, which I call f, because the convolution of two functions is commutative. This is the commutative property. This is the property that makes solution of these little problems possible. If not, then it will depend on the order in which I choose, and that will make no sense. So in other words, what I'm saying in this particular example is h of t is equally correct to write h of t as instead of pretending that the function of t minus tau is g, I can pretend that this is f of t minus tau g of tau d tau, in which case this integral is 0 to t minus tau sine omega tau d tau. Okay, so I invite you to let's call this a and let's call this b. Evaluate both these integrals and show that they are indeed the same. Okay, so you should find something like at minus sine omega t divided by omega square. That is the answer. So you can go ahead and check this. So the commutativity is an interesting property. So let me actually show that this makes sense. So suppose if I take the convolution of f and g, I write this as 0 to t f of tau g of t minus tau d tau. Here I don't have a choice. Once I choose f on the left hand side and g on the right hand side, this is how it is defined. But on the right hand side, I can always make a change of variables. I can choose a new tau prime, which is t minus tau. Okay, so which tells me that d tau prime would be minus d tau. And when tau is 0, t prime is t. And when tau excuse me, when tau is t, tau prime is 0. So f convolution of g, I will write in this change of variables. So the limits are tau prime. So when tau is 0, tau prime is t. When tau is t, tau prime is 0. Tau becomes, so tau is now t minus tau prime. So this is f of t minus tau prime, g of tau prime, and d tau is minus d tau prime. And I can get rid of this minus sign and switch the order of integration. So I can write this as 0 to t, f of t minus tau prime, g of tau prime, d tau prime. And since tau is a dummy index and tau prime is also a dummy variable, this is basically the definition of the convolution of g and f. Okay. So the convolution has certain nice properties that you can always exploit to solve simple problems. So let me list the 4 properties of convolution that are relevant. The first is what we've just discussed. F convolution G is G convolution F. This is commutativity. And if you take the convolution of F with a sum of 2 G's, this is basically taking the convolution and then taking the sum. This is associativity. And it doesn't matter in which order you take the convolution, as long as you respect left to right. So this is basically F star G star V. Okay. And then of course, if you take the convolution of F with 0 or 0 with F, you get 0. If you think the last property was a little silly to state, notice that the convolution of F and 1 is not equal to F. Okay, so it's always important in mathematics to spell these things out literally, because there might be cases where you could be surprised. For example, choose F as cosine t. Okay, so what is the convolution of F and 1? F convolution 1 is 0 to t, f of tau cosine tau. 1 is just a constant, d tau, and this is sine t. So the convolution of f and 1 is sine t and not the function itself. Okay. So this is important to know. This is a certain unusual property of convolution because of the way it is defined. Okay. Now, before we wind down, I will point out yet another practical aspect of this convolution and where it can be useful. Okay. Example. Solution of inhomogeneous equations. I'll work out a very specific example to tell you how to actually use this. So let us take a very simple example. Y double prime plus 4y equals g of t. Okay. And you have figured out many methods to solve this equation, right? So if you could use the method of undetermined parameters once g of t is some cosine t or e to the I omega t or anything very simple like that. Or if it is not, you could use variation of parameters, or you could use series solutions. We have taught you many methods of solving equations of this kind. But suppose if g of t turns out to be a little tricky, then you could also use Laplace transforms, right? So as long as the Laplace transform of g of t is not extremely complicated, you might be able to do this very simply. So let us turn this into an initial value problem. Y of 0 equals 3 and y prime of 0 equals -1. And then your goal is to solve this using Laplace transform techniques, and you know how to solve this because you have solved many examples. So you go ahead and do this. Okay. So let us say that the Laplace transform of little g is some capital G of S. Okay. And then you apply the formula and you find the left-hand side is S squared times y minus S y of 0 minus y prime of 0 plus 4 times capital Y is some capital G. Okay. And then you quickly see that y of 0 is given as 3 and y prime is given as 1. So put everything together, s squared minus 3s minus 1 plus 4y equals capital G of s. Okay. And then you write this as s squared plus 4 times capital Y equals 3s plus 1 plus G of s. Then you're done. This is your subsidiary equation. So the inverse Laplace transform, the Laplace transform of the function that you're looking for is 3s plus 1 over s squared plus 4 plus G of s over s squared plus 4. Up till now, I've not done anything new. This is all something that you have already done. So y of t is obviously L inverse of 3s plus 1 over s squared plus 4 plus L inverse G of s over s squared plus 4. Even this is things you have already done before. But here the question is, suppose if capital G turns out to be a little tricky and you're not able to evaluate this inverse Laplace transform easily, what do you do? Now, the first guy is rather straightforward. I hope you find it straightforward because you can write this as, this is 3 times s over s squared plus 1, which is basically cosine 2t. Okay. And then minus 1/2 sine 2t. That is this guy. The second guy I will write as 1/2 L inverse of 2 over s squared plus 4 times capital G of s. Now, capital G of s is some very difficult thing. Let us say e to the minus s times, I don't know, 1 over s squared plus 5 times some complicated polynomial, whatever it is. Suppose I give you something very mean and evil. You don't have to know what capital G is. What the Laplace transform of inverse Laplace transform of capital G is. You can simply use convolution because you have factored this into 2. You know what this guy is, right? The inverse Laplace transform of that guy is basically sine 2t. That is something you know, which means your answer can be written in a very simple form. You can just leave it as an integral. Minus 1/2 sine 2t. You can evaluate it as an integral, I mean, plus one half 0 to t sine 2 t minus tau g of tau d tau. So notice that the advantage of using the convolution method in this particular fashion is that I never had to use the explicit form of capital G. Suppose if I give you a driving force whose Laplace transform is very difficult to figure out, this capital G, you just use it as some capital G and then use the convolution at the end, hoping to heavens that you can actually use the convolution. Okay. So in this case, in this example, I could use the convolution because the way the subsidiary equation came out to be was such that it was something times capital G, and the something was something whose inverse Laplace transform I knew exactly. It was sine 2t. So there could be problems that can come under this category where the Laplace transform itself is difficult to find, but the way the subsidiary equation works, you can actually figure out the inverse Laplace transform of a more complicated function. Okay, simply because you already know what the driving force is. So convolution can be used in a judicious manner for those problems for which you find the traditional techniques to be a little difficult. So it's actually of enormous practical use. Okay. So I'll stop here for today, and then if you have any questions, you can ask. We'll not be covering anything else in the subject of Laplace transforms.